I would like to acknowledge the traditional custodians of our country throughout Australia and their connections to the land, sea and community, and pay our respects to elders past, present and emerging. Alrighty, today we're welcoming David Whitmore to our virtual stage, who will be talking about design considerations for galvanic anodes. David is President and Chief Innovation Officer of Vector Corrosion Technology, a company which specialises in the repair and corrosion and protection of reinforced concrete structures. David is a registered professional engineer and NACE cathodic protection specialist and serves on a number of repair, corrosion, sustainability and education committees across ACI, ICRI and NACE. Over the past 20 years, Vector Corrosion Technologies has gathered a huge amount of data on how galvanic anodes perform, age and protect steel in reinforced concrete structures. Some of the variables that influence performance can include environmental exposure conditions, moisture, temperature, and other factors such as the surface of the mass ratio of the zinc core and the zinc core activation method. In this method, David is going to go beyond the data sheet to explain just how these factors govern the service life of zinc-based cathodic protection systems and how this information can be used to design durable galvanic protection systems. For questions and answers, there will be time at the end. Please feel free to answer your questions via the Q&A tab at the bottom of your screen. If there's any pressing questions which should be answered straight away, David, I'll jump in. Otherwise, perfect. Keep those to the end. All right, and over to you, David.
Well, great. Thank you, Kieran. Thank you, ACRA, for supporting these educational webinars. And good morning to everyone that's on the line. The topic today is to talk a little bit about design considerations when you're using galvanic anodes. And just to get right into it, really there are four aspects that I'd like to talk about today. The first is just very briefly, what are galvanic anodes and why are they used? Second, which is going to be one of the main technical portions, is talk about design considerations and some of the different things that should be considered when you're looking at an active design, and particularly if you're designing for long-term performance. Number three, talk a little bit about anode selection and spacing. That will pretty much flow out of the design considerations portion of the presentation. And then at the end, I'd like to talk a little bit about prescriptive versus performance-based specifications. And I think we will see that we're, at least in North America, we're moving more and more towards performance-based specifications for the use of galvanic anodes, but also a whole bunch of other things related to concrete repair. So just to start at the beginning then, what is a galvanic anode? Galvanic anode is basically consists of some type of galvanic core, usually zinc-based for anodes that are embedded within concrete. Some means to electrically connect the zinc to the steel, such as the tie wires illustrated here. And in all the cases that I'm familiar with, you're going to have some type of cementitious or some type of active matrix that surrounds the zinc core. And the purpose of that is to keep the zinc core actively corroding over time. And those are the main components in a galvanic anode. Now, when you do a concrete repair in a perfectly ideal world, the concrete repair should match the existing parent concrete and should blend right in terms of all physical, mechanical, and electrochemical properties. And if it does that, it's going to be ideal and it will last an indefinite amount of time. In the real world, however, when we do a repair, very often we're doing a repair because the concrete is either chloride contaminated or carbonated. We remove a portion of the affected concrete and replace it with chloride-free repair or uncarbonated concrete. And we end up leaving a couple where we still have some chloride contaminated concrete or some carbonated concrete remaining, coupled with the repair, which presumably doesn't have either of those issues. And we will create a corrosion cell between these two different environments. And the chloride contaminated or the carbonated zone will be the area where corrosion continues. And that occurs because we have a difference in potential between the chloride contaminated concrete that remains in situ and the new repair, which presumably has no chlorides, and it will be these potential differences that drive corrosion. Now, you've probably all seen examples of this. The photograph on the left here shows a couple of columns on a marine bridge. And you can see repairs that have been previously completed here. And you'll notice in the areas around the repair, and similarly on this one back over here, the delamination area has been marked out on the concrete because this area has continued to corrode, and maybe in some cases even corrodes worse after the initial repair is done. And this is a deck application, which you probably don't see so often in Australia because it's because of de-icing salt application. But the same thing, you have a series of different repairs, and the adjacent areas tend to continue to corrode. Now, the most common application for galvanic anodes is galvanic anodes in localized repairs. And the reason that galvanic anodes are used in these applications is because, assuming the galvanic anode remains active, its electrochemical potential is going to be more negative than the steel inside the concrete. And when I say that, I mean it should remain more electronegative than the steel within the repair itself, which may have a potential, as we showed earlier, maybe around -200 or something in that range. Or it should remain more negative even than the steel that's in the adjacent chloride contaminated concrete, which may be in the range of -300, -400 millivolts. And as long as this is more negative than the adjacent steel sections, then current is going to flow from the galvanic anode to the steel, and corrosion in the steel section will be reduced. Okay, so just a few pictures, in case you haven't seen these used in the field. This is a picture of some repairs on a marine deck where concrete's been removed up to a curb area, but this section of the concrete is not removed, and because of that, chloride contaminated concrete remains in place here, and a line of galvanic anodes is installed along the edge of this repair to protect for this incompatibility that's being left in place. Here are a couple of pictures. The left one is a bridge in Australia. The right one is a bridge in the UK. You can see a repair on the underside of a beam over in a marine bridge here. This is in New South Wales, and you can see some galvanic anodes have been installed to basically mitigate the ongoing corrosion, or at least slow it down. And in the one on the right, concrete repairs and joint replacement is being done. And again, chloride contaminated concrete is being left in place. So the anodes are being installed to mitigate that issue. One other area where we see application for galvanic protection, and the principles that we're going to talk about here today also are applicable, is where you are building something new, such as this. This is a bridge widening for a marine bridge out on the west coast of Canada. So this is out in the Pacific Ocean. And they're adding a lane onto each side of this bridge. So they've removed the existing, they're removing the existing parapet wall that was here. I guess there's a delay in my pointer, so I'll just quit moving it around. And because they're not removing all of the existing concrete, the existing concrete is going to still have a residual level of chlorides, and the new concrete out here is not. And so the same thing happened on the retaining wall that you see to the left. A new concrete section was added above an existing section of the wall, and Basically, there's no chlorides in the new section, there's chlorides in the lower section, and you can see clearly that there's serious corrosion going on, particularly along the interface between the new and the old because of the chloride to no chloride, because of the potential difference that is created there. So a simple solution here is to add a line of galvanic anodes along the interface between new and old to mitigate that corrosion risk. And then in addition to localized or discrete galvanic protection applications, there may be situations where you wish to have more of a blanket protection over the entire structure or an entire section of the structure. Could be like either of these examples that you see here, but here the intent is generally more to provide full cathodic protection, galvanic cathodic protection to the whole element, a deck as illustrated on the left or a substructure on the right. For that, you're basically going to use the same principles that we're going to talk about, but you're going to use higher current densities and higher, obviously, polarization parameters if you're talking about cathodic protection criteria. Okay, so getting into the design side of things, in terms of anode selection and spacing, a lot of things have changed from over the last 20, 22, 23 years. From a vector perspective, the first version of the product that we are selling today came out introduced to the market in 1999. And at that time, there was a single kind of a standard size. There was only one size, galvanic anode. And by the time you get 20 years later, we had 4 standard sizes. We had done some improvements with regard to the zinc cores and also to the chemistry of the embedding mortar, not the embedding mortar, the activating mortar that surrounds the zinc core. And all of those things were done for a reason. And we're going to talk through why those different things were done to improve and have more reliable performance. So today, there are a range of sizes that are available. And very often when people talk about sizes of anodes, they really focus on the right-hand column here, which is zinc mass. And they say, okay, how many grams of zinc is your anode? With 40, 60, 160, 330, those are the current standard sizes that are available in our range. And although zinc mass is important, it's only one aspect. And as you'll see, it's not the only thing that relates to the design. But clearly the bigger anodes with more zinc and more surface area will put out more current, and you can use those for protecting more steel. Okay, so what factors play a role in influencing the design? One factor is the surface area of the steel to be protected. That's a big factor. Of all of the things, I guess you can't say one thing is fundamentally more important, but obviously the more steel area you have to protect, the more current you need in order to protect it. And so that's one thing that you need to consider. A second thing that you need to consider is how corrosive is the environment. The more corrosive the environment, the higher the amount of current that you require in order to protect the steel. And some of the factors that influence corrosivity of the environment are chloride concentration, the degree of carbonation, the temperature, among other things. And then the third thing that you need to think about when you're doing design is you need to think about what level of protection is required or what level of protection do you desire to achieve. And so depending what level of protection you want, that's going to influence your choice of for example, design current density. So starting at the top of this list, steel surface area to be protected is an important factor. And if you're going to go back to design basics, then you can calculate the total steel surface area for each individual job that you are doing, and then work back to basic principles to calculate the total either number of anodes or the total quantity of zinc that is required in order to provide that degree of protection to that total amount of steel. And you can do that on every individual project. And theoretically, that's a perfectly fine way to go. And for complicated things, we still do that today. But if you have a section that is more standardized, for example, if you are dealing with beams or if you're dealing with decks or abutment walls, and you can look at the element in a planar view, like an elevation or a plan view, and you can calculate the amount of steel surface area per unit area of concrete, then you can calculate a steel density ratio, as kind of described in words at the upper portion of this slide. If you can do that, then you can calculate anode spacings and things like that, that then can be applied to any type of structure or any portion of the structure that has the same steel density ratio. So for making your calculations simple and not having to do detailed calculations for every individual, so many square meters or square centimeters of steel that you're dealing with, you can break it down into steel density ratios and have a much simplified design procedure. And so calculating the steel density ratio basically involves calculating the surface area of each individual reinforcing steel bar within the footprint that you're talking about, which is simply, pi times the diameter times the length times the number of bars, and do that for each different size of bar that you have. And, in Australia, as we do here in Canada, we would typically use 1 square meter as a typical concrete footprint. So we'll calculate the square meters of steel surface area embedded within 1 square meter of concrete surface. And if we're doing the same calculations in the States, because they work in the old English units, we will do the same thing, but square feet of steel relative to 1 square foot of steel surface area. And there's no need to tell you what is pi or anything else. So if we go through these calculations just as using one as an example, and there are some design tools that if anyone wants at the end of the webinar, you can send me an email. I can send you some calculation sheets, but this is just one example. If you look on the right-hand side of the example for the metric version of the calculations here, I have picked, just as an example here, a heavily reinforced bridge deck slab. And I've assumed that there are 15 millimeter diameter bars at 200 millimeters on center in each way, and that there are 2 mats, an upper mat and a lower mat of bars. And so to calculate the total amount of steel within a square meter of concrete, we're going to look at the top mat of bars in one direction. I picked the longitudinal direction first. And so pi times d times L times n, we calculate, that we have 0.236 square meters of steel in that direction per every square meter of surface area. We do the same thing in the transverse direction for the top mat of steel, and we get the same number because we've used a similar spacing in both directions. And we do the same calculation for the top bars or the longitudinal bars in the bottom mat, and then we do the same thing for the bottom or transverse bars in the bottom mat. And then we add all of those things together, we get 0.94, and I just rounded it off to a steel density of 1 square meter of steel for every square meter of concrete surface area. And we're talking about steel surface area, not steel cross-section area here. Okay. So once you have the steel area or the steel density, then you need to then select what are you going to use for your design current. What do you need as a current density in order to provide protection? And that number is going to depend on what level of protection that you're trying to achieve, as well as the physical condition, such as the chloride concentration of your concrete. So for these examples here, I'm just using the current required to prevent corrosion for cathodic prevention purposes. If we were doing cathodic protection, the design current density is going to be about an order of magnitude higher. And EN 12696 tells us that to prevent corrosion, we need a current density somewhere between 0.2 and 2 milliamps per square meter of steel surface area. And although that's useful because it's a number, it's a pretty wide range, it's an order of magnitude. And so should you use 0.2 or should you use 2? It depends on what your conditions are at the job site. So in our design tables, we actually use a minimum of 0.4 milliamps per square meter for chlorides that are moderate, which we'll talk about in a moment. We're using basically 0.8, so current densities between 0.4 and 0.8, but we're using actually 0.8, where you've got slightly high, like a high, moderate to high level of chlorides. And we're using current densities of 1.6 milliamps per square meter when we have chloride concentrations that are a little bit higher. And the reason we're using those current densities is just based on data that's been collected in the literature. So instead of using a standardized number for all applications, we're actually varying this current density that we're using based on the chloride concentration. And I think there's a good rationale for doing it. Not only does it match stuff in the literature, but if you go to the BRE Digest 444, where they took a look at corrosion risk or probability of corrosion as it relates to chloride concentration, we see more or less the same 3 zones developing. You got a low to moderate risk zone, you could say moderate to high risk zone, and then an extremely high risk zone, and they correlate with different levels of chloride. And so just to summarize what I've said on the last 2 slides, in our standard design tables, we are using the level of chloride in the concrete as the parameter by which we, it's the default parameter that we use in order to select the current density that we're using for design purposes. So if the chloride level is 0.8% or less, then we're using a design current density of 0.4 milliamps per square meter. If it's between 0.8 and 1.5, we're using a design current density of 0.8 milliamps. And if we're above 1.5, then we're using a design current density of 1.6 milliamps per square meter. And again, these are for cathodic prevention applications. If we take the information then, and you then go to the standardized spacing charts, there will be different spacing charts for each corrosion risk. And I just happened to pick the middle range here, so 0.8 to 1.5. And if we go to a steel density of around 1, which we calculated before for the steel density for this bridge deck example that I just showed you, at least with regard to our galvanic anodes, which, I'm just using those as an example, you have 3 options. that will come out. Well, you have 5 options, but 3 different spacing charts. You can use, the smaller anodes at 200 millimeter spacing. You can use kind of the middle-sized anodes at 325 millimeter spacing. You can use the larger anodes at 425 millimeter spacing. All 3 of those options will give you the same current density to the steel. Obviously, you'll need more smaller anodes in order to achieve that and less bigger ones, but they're going to provide the same level of protection to the steel. And that's then a choice for the user to determine which one do they prefer to use, more small ones or less big ones. But the protection will be the same. If you want to take a look at it more from a theoretical point of view, I just wanted to let you know that the spacing charts are actually built off of the calculated spacing curves that you see here. and the calculated spacing curves, my apologies here. Okay, the calculated spacing curves here. There's one spacing curve for each of the sizes of anodes. And obviously the spacing is less for the smaller anodes, moderate for the bigger ones, and higher for the larger anodes. And that's to give the same current density to the steel, because everything in this table here will be where you have like high risk. So the 0.8 to 1.5% chloride applications. Our steel density, if you look at what we talked about, is 1. And if you go back to the calculated spacing curves, it's going to tell you that you can use a spacing that's a little bit wider than what I showed you in the last set of tables. And the reason for that is because these tables give you the steel spacing, or the recommended spacing, maximum spacing, based on a range of steel densities. Our calculated steel density was 1 in the example, and our range that's covered in this line of the table is 0.9 to 1.2. If you're doing a really large job or something, then maybe this is useful to say, well, instead of going 200 millimeters on center, I can stretch it and get 220 or 230, whatever this is. But if you look at it, 1.2 is basically here. And so the spacing that's in the charts is based on the maximum steel density for that range that you're talking about. So at 1.2, you're going to get a spacing of 200 millimeters on center for the smaller anodes, all the way up to whatever it was, 425 or something for the larger anodes. It's because you're looking at this line in the chart. And so that can be something that you can think about when if you're involved in a big job. But don't fool yourself about trying to be too precise about this, because there's lots of other things that are varying in the field. Okay, so there are a bunch of other assumptions that are built into the spacing charts. And it's important that you understand what they are, at least you're aware of what they are, and you can decide whether that's appropriate or not appropriate for your project that you happen to be looking at. So this is a little graphic kind of illustrating a view of a repair. And so I think I'll just kind of try and walk through these as simply as I can. So the chart is going to tell you a spacing, and obviously the spacing is going to vary depending on factors like the steel density, etc. The design current density, as I said before, is, whoops, it's jumping all over here, is basically either 0.4, 0.8, or 1.6 milliamps per square meter. Those are the default design current densities in the tables. And those design current densities are calculated to the reinforcing steel at a position that is halfway between the anodes and 100 millimeters outside of the repair. So at this location here, or this location here, 100 millimeters into the parent concrete, kind of halfway between the anodes, that's where the design current density is calculated. If you were to look along a bar at this position here, directly opposite to the anode, the current density going to the steel at that location would be higher than the design current density. And obviously, as you move further away from this point, the current density of the steel will be decreasing. And as you move closer to the repair, the current density of the steel will be increasing. The spacing charts also assume that the concrete resistivity is 20,000 ohm centimeter, which I think is a fairly reasonable or conservative assumption if you're dealing with chloride contaminated concrete. That may be somewhat different if you're dealing with carbonated concrete. And the assumption built into the spacing charts is that the resistivity of the repair material is 50,000 ohm centimeter, which is the maximum resistivity that we allow. And so that's kind of the worst case scenario that the chart is built on. Okay, another thing that is built into the charts, and another thing just that we need to just talk about and get a common understanding of, is how is the current output from the anodes behaving over time? And this is probably the most important part of the webinar. And if you take an anode and you install it into a piece of concrete and keep it in a uniform environment, you know, in, for example, a laboratory or something where it's inside of a building where it's not changing, you know, current's going to start out, it's going to drop with time. That's inevitably going to happen with galvanic anodes. And you will, based on everything that we've seen, you'll see a shape like this, a curve that's kind of shaped like this. It's decreasing with time, and it's essentially an exponential decay curve. If you look at data from a real site in the field, and this happens to be from a bridge in Ohio, the orange line is plotting temperature. So this is summer and winter and summer and winter, and you see a few years illustrated here. And I apologize, it's in Fahrenheit because it's an American project. And the blue line shows the current, which is high in the summer, low in the winter, high in the summer, low in the winter. And so there's a lot of up and down that happens with the seasons and the weather. But if you look at the overall trend that's happening, you'll see that if you get rid of the weather effects in there, if you average them out, that you're going to get that same kind of exponential decay curve. And that is really important because we can use that knowledge in the design process. If we take the current, even if it is current that's been collected from a field site, so it goes up and down with the weather, if we have it over a period of time, you can get rid of the weather effect out of the data. And if we plot the data, instead of just being current versus time, we plot the log of current versus time. On anything that we've seen, you will get a nice straight line kind of relationship. And obviously the weather will affect that up and down, but you're going to have this decay curve can be translated into a constant slope when you plot log of current versus time. And when you calculate effectively the slope of that line, we get what we call an aging term. And that is essentially the amount of time that it takes for the current to drop by 50% from either the initial current or from that particular point in time. And so for the anodes that we are currently producing, we have an aging term of around 13 years. So every 13 years, the current output from the anode is going to drop by 50%. And in the next 13 years, another 50% of what's remaining, and another 13 years and whatever, until obviously eventually it doesn't work anymore. And so we can use that long-term behavior, and we can say, okay, if we start at a current density here, after a certain period of time, we've cut by 50. And then after another period of time, we've cut that by another 50%. So if you go up to the table, if we start at 2 milliamps per square meter, after 13 years, we're down to an average of 1. If we go to 26 years, we're down to 0.5. And obviously there's some numbers filled in between here, but that's the behavior. And once you understand how that behavior works, then you can do a design with that in mind. And so in addition to a couple of the other things that we've talked about that are built into the standard design spacing charts, we are assuming in the standard spacing charts a 20-year anode design life. We're assuming an aging term of 12.5 years, which is just a little bit more conservative. We are assuming that the minimum current density that we talked about previously, illustrated over here, that is the current density that's going to be provided to the steel on average at the design service life. So at 20 years, if we're in this category here, here, then we're looking to have 0.4 milliamps per square meter to the steel at 20 years from initial installation. Okay, and we'll show you that in a couple examples in a moment. We also need to think about temperature, which I'll come back to here in a second, and how that influences things. And then obviously we can do custom designs. So everything that I'm showing you is based on data for our anodes in the kinds of environments where we've been selling them and monitoring the performance. If you're going to use other anodes, then you just need to make sure that you get data that is for the anodes that you're doing the design for. These are a couple of different ones that we were able to find some data on that was published. In these two examples, the aging factor was less than 12.5 or 13. And that, you might say, well, does that really make any difference? And I would say, well, it depends. So in the illustration that I was showing you the first part of, if we have a design intent to provide 0.4 milliamps per meter squared of current to the steel at 30 years, and make up whatever example you want, but that's what this one is based on. Then, this alternative, which is, behaving differently over time, even though it starts out at the same initial current, is, dropping to the design current density here in less than 5 years. Now, if it has a longer aging term or aging term, then 13, then this line is going to be more flat, and you might be able to start at a lower current density and still have the design current that you want at the design life for your anode. So you just need to establish what you want to achieve and then design in order to achieve that. So this slide here really summarizes kind of what we've been talking about over the last few slides. You can monitor the current versus time. That translates directly into zinc consumption with time, which follows the inverse of the first curve. And beyond that, I think we've talked about most of those points. Considering the time here, I just want to make sure we get through and talk a little bit about temperature. Temperature is a really important factor, and current output from anodes varies a lot with temperature, and you can see that in the field data. If you plot the log of current versus 1 over the temperature in degrees Kelvin, then you'll get a nice straight line like one of these, and the slope will be pretty consistent, at least for a certain type of anode. That slope will be consistent, and we see that current doubles from the anodes about every 10 to 15 degrees Celsius that the temperature goes up, and so that's an important thing to take into account. So I just said anode current doubles when the temperature increases. Corrosion rate of the steel also increases by about the same factor. So basically you need more current to protect the steel when the temperature gets hotter anyway. So it's not wasted, but it is going to use up zinc more quickly. For temperatures that are 15 degrees average or less, there's more than enough zinc there to last 20 years with a little bit of buffer, and stay above your design current density. But when the average temperature is higher than 15 degrees C, and particularly if it was higher than 20 or maybe even a little more than that, then you for sure should be taking a look at the temperature and how that's going to impact your service life. So we do make some anodes that are specifically designed for high temperature environments. They have more zinc mass, but maintain the same surface area. So there's just more mass available, but they won't put out any more current. And you know, they are primarily used in the portion of the world here that's illustrated in red, which is basically anything that's, you know, kind of 20 degrees Celsius average temperature year round or higher. You know, if you're in the northern part of Australia, northwestern part of Australia, you're definitely in that zone. You know, Sydney, you're above 15, but you know, maybe not significantly above it. You could take that into account a little bit, but certainly if you're moving more into Asia, India, Middle East, South Florida, or whatever, you're going to run into those issues. And I didn't point this out on the previous time I showed you this slide, but if you look at the very last column over here, so we have, I said, the larger anodes, you know, there's actually 2 of them listed here, XP4 and XPX. Both of them will have the same spacing for the same condition, but XPX has twice as much zinc in it. So it will last longer in applications where you have very high ambient temperature, or you have, you know, very corrosive environments. Okay, so just wanted to say that everything I've showed you is kind of based on standardized, kind of simplified design, but any of the designs can be customized. You can vary any of the factors that we've talked about. You know, current density, for example, anode service life can be changed. You know, aging factor, environment, any of these things can be changed from what's the default in the spacing or in the tables, in the standard tables. And if you're doing a large project, particularly if it's going to be done over a number of years, it may be appropriate to install a pilot installation and monitor and get some data from your exact project, your exact conditions, and be able to use that to refine your design on other phases of the work. In terms of specs, currently, most specifications that I see are prescriptive, and they're very often focused on zinc mass. And it's not that zinc mass isn't an important factor, it is, but it's not the only important factor. And zinc mass alone is not predictive of the performance or the long-term performance in particular. A lot of other things play a role there. So in terms of performance-based specifications, I think over time we'll see things move more in the direction where we have specs like this. Basically you're going to say, the anode shall deliver a minimum current density of some number, which you can select, but these are the 3 defaults that we've talked about already. To the reinforcing steel for the specified service life. ACI, which is the ACI 562, which is the concrete repair code, has introduced this concept, and it's quickly gaining adoption, certainly in North America, where a specified design life for repairs is required. And so having a certain current density for a specified design life will flow out of that. And then having that performance data based on, or using performance data to justify your design is also flows out of the format that ACI 562 is currently using. We talked, and the examples I showed you to try and keep it simple so that we can talk about it are showing discrete anodes in kind of repairs or other similar applications. You can use all of the same principles. If we look at distributed systems, the difference here is that you're more likely looking at cathodic protection criteria instead of cathodic prevention or corrosion prevention criteria. As I said, we can use the same principles and the same approach as we've done in all of the previous slides. We're going to need to provide sufficient current to polarize the steel that's usually significantly higher than the design current you'd use for cathodic prevention. Similar to the examples I showed you, we need to consider the corrosivity of the environment and to adjust the design current density accordingly. We need to define the design service life, which again is consistent with ACI 562. We need to consider the behavior of the anodes over time, because we need to consider the performance at the design service life, not just at the initial time of installation. And we need to also consider the in-service temperature, particularly if you're putting these in a place that's consistently hot and humid and salty. That's even worse. And zinc mass alone does not determine performance. I think I've noticed that there's been a couple of things. Are there a number of questions there, Kieran, or do I have a few more minutes to scan through a few more slides? I don't want to run you over.
David, we had one question come through, and I can drop it in now. I was going to wait a little bit later,
sure.
But it's just more about if some is good, is more better. Like, is there any problem if we be overly cautious and put additional anodes than what we've calculated? And is a bit more okay, and then a lot more is bad?
Well, at some point it probably just becomes either not cost effective, or you may be accused of wasting money. But from a protection point of view, it's not going to be bad. You're probably going to get a higher level of protection than you may be designing for, which isn't inherently bad, but it may not be the most cost-effective approach. Because they're galvanic and there's a limited potential difference between the zinc and the steel, you will polarize the steel more with more anodes. Obviously, that's what we're doing with the distributed system. You're polarizing the steel sufficiently to meet full cathodic protection criteria. But because they're zinc-based anodes, there's really pretty low risk of, you're not going to have any issues with, hydrogen embrittlement or those kind of things that you might otherwise run into if you try and, run an impressed current system too high. I'd say the biggest risk is that you waste money unnecessarily.
Oops, we have another one. Do you expect a distributed galvanic system to meet depolarization standards? such as 100 millivolts after 24 hours? And what are the limitations, such as concrete resistivity? And do you happen to have any data around the uniformity of polarization given the large spacings you are specifying?
That's a really good question. Well, let me just go through a couple more slides because I can answer that. And I'll just show you a couple of examples. I'll show you, I had two examples here showing distributed galvanic protection. This happens to be a bridge abutment, but I've seen very similar applications we've done on marine structures as well. Chloride contaminated, badly deteriorated. Basically, they did a resurfacing with galvanic anodes built into the concrete refacing. Transport New South Wales has done a few jobs like this using this approach. You can see the anodes here are these red colored bars in this particular case. They're embedded in the concrete overbuild there. And I had showed you some of this data back in the one slide. So you can see this is a few more years there, but the anodes continue to put, these are now over 15 years old. We've had failures of the data loggers, but the current's still flowing even through this times when it's not being measured. And in answer to your question, or the person, whoever was asking the question, this system was designed for galvanic cathodic protection to meet the standards here, which are pretty similar to what they are in Australia. 100 millivolt polarization is the minimum required under the NACE standard. And it has consistently been over 100 millivolts of polarization throughout the entire protected area for, well, it's 10 years of data shown in this slide, but it's over, we have 15 years of data. And yes, so the simple answer is yes, you can, you just need to design for the parameters that you have. And with galvanic systems, you have a limited driving voltage. And so you need to manage the circuit resistance in order to achieve the polarization of the steel. And if you do that, you can design, I mean, we've got dozens of jobs that are, meeting either the NACE or the European standard for cathodic protection in terms of primarily the polarization criteria, although in some cases you might be achieving the instant off potential criteria as well. So any other questions? So that's just
this one is a little bit tight there. Is there any can galvanic anodes affect the coating on the concrete, resulting in any flaking or discoloration of the anode location?
Coating on well, I'm not sure what the question, I'm not sure what kind of issues. I mean, so we do impressed current cathodic protection. Obviously we do galvanic, which we've been talking about here today. I mean, I have seen situations with impressed current, particularly with discrete anodes or with ribbon type anodes, where because of gas generation at the anode, we've had some bubbling on coatings. But that's because you're generating gas either at the anode or at the steel. You should not see that with anything galvanic. Generally, you don't have enough voltage to do that. You're going to have proper surface preparation so you don't have, delamination or bubbling. But I don't think that should be an issue that would be unique to using or not using the anodes inside.
All right, that's all the questions at the moment. So feel free to carry on.
Sure. Okay. Well, I'll just show you a couple more slides. So, I mean, that was one project example that I showed you, and that based on the monitoring that's being performed and the whatever, there's a 35-year estimated service life for that system that's installed on those abutments in that particular case. And although I don't have any long-term data, I thought I just threw this in as a last example. It's showing the same concept. It's on a project that is going on right now. The first phase of it was completed relatively recently. And what they're doing in this particular case is that they are doing accelerated replacement of the bridge in question here. It's a long section of elevated expressway, very deteriorated because of chlorides. And in order to do this accelerated replacement, they are reusing, they're basically repairing and reusing all of the existing substructure, some of which is in horrible condition. And here you can see one of the pier caps, which is very badly deteriorated because of chloride-induced corrosion. And the technique that they're using here is similar to what I showed you from the Ohio DOT job. The contractor is responsible for going in and removing the existing concrete cover down to the top of the reinforcing steel within the section of the columns and the pier caps. But they are not allowed to chip behind the bars and lose the confinement that exists from the steel that's there or that's remaining there. And then they are forming and pouring a slightly larger section, which includes galvanic protection, which you'll see. And the galvanic protection that's being installed is designed for to provide full cathodic protection for the steel that remains in this section. And here's a picture kind of during construction. You can see the concrete cover's been removed down to the steel. The galvanic anodes here are these horizontal strips that are in here. There's a layer of galvanized welded wire mesh there for crack control. And the section is formed and poured back. You can see a section of the pier cap here is poured, and this section is being formed, but is not yet poured. And if you take a look, this was last fall near the end of that section of the expressway. So this is being done over I think it's an 8-year period. This project is a long section of elevated expressway, and there's a section being done every year. And so inside all of these rehabilitated substructure elements is the existing reinforcing steel. The chloride contaminated core of those columns is still there, unfortunately, but the galvanic cathodic protection system is there to deal with the fact that you're leaving chlorides behind. And so it's a way that they are able to repurpose the substructure and able to do the rapid bridge deck replacement without shutting down to traffic for an extended period of time. All that work is being done. All the work on the deck is being done at night, and there are no complete closures during the day on the upper portion. So just to kind of wrap up,
David, I might just quickly.
Sure.
Is there any reduction in the requirement of cover if we're using galvanized reinforcing or galvanized mesh? Does that have an effect on the cover required?
Oh, that's an interesting question. I don't know the answer to that. I mean, it's not that common. There are a few agencies over here that are using galvanized rebar instead of reinforcing steel for all applications. For example, the New York Thruway, which is the tollway authority, has a flat specification for galvanized rebar. But as far as I'm aware, they are maintaining the same normal, typical concrete cover. In the example I just showed you, the cover over the galvanized wire mesh there would be less than kind of what the original cover was in the concrete, because it's on the outside face of the anodes. At best, I would say it's probably 5 centimeters of cover on the galvanized mesh there. Yeah, that's an interesting question. I'm not sure that there's a code requirement for that. I'd have to ask one of my structural friends.
I just in that just that prior example,
Yeah.
one of the questions was why galvanic and not impressed current?
Okay, no, that's a valid question for sure. I mean, they could have gone with impressed current. Technically, impressed current would be perfectly fine. Maybe even cheaper in some cases. The owner has a very strong desire not to have ongoing maintenance on the structure, and you can either agree with them or not agree with them, but was very clearly kind of expressed by them, and that was probably one of the main drivers there. I mean, they've done impressed current in the past, and it's not that it hasn't worked, but they haven't done a great job of maintaining some of the systems. But technically, it would be a perfectly fine solution.
You know, I've had experience in the past where an impressed current was probably the better solution, but the client has been adamant that they just know their people and their systems, and the system is just not going to get maintained, or it's going to get turned off for a reason and not get turned back on. And they know that it's great in theory, but it's going to be a waste of money for them because they know it's just not, they can't get there.
Yeah, they may not have used those words, but I think that was part of the message that was passed on to the design team that was involved in this job. I mean, we weren't the designer for this job. It was one of them big 5 engineering firms, but they clearly had a mandate from the owner.
And from that example, from the same person as well, the monitoring system. Is there a monitoring system for galvanic?
Oh yeah, for sure. I don't have any pictures on this particular one. If you go back here, just as an example, here's a monitoring station. One of the monitoring stations that was put in on this project. And I mean, you can monitor any galvanic system the same as you can monitor an impressed current system. The only difference is there's no actual rectifier here. The monitoring station, you've got, instead of these anodes being directly connected to the steel, the wires come out of the concrete, into the monitoring station, and then the wires go back from the monitoring station to connect to the steel. So you just have an external point where you can take your measurements if you're going to do it manually as a manual monitoring station, or in this case, there's a data logger inside the monitoring station. And as long as the batteries haven't run out on the data logger, you're collecting data. But you can see here, there's some gaps in the data in the blue line. That's because the data logger for the current monitoring, died for whatever reason. It could be batteries, or it could be for other reasons. But the system's still running in these gaps. Like the anodes are still electrically connected to the steel. It's just, you've quit measuring what it is between these gaps that are existing in the curve. And same thing happened for a period of time in the temperature data logger as well, for reasons sometimes we understand and sometimes we don't. But yeah, you can monitor any of these systems, and you should monitor them to make sure that you're meeting whatever performance criteria you're looking for.
That's it from the questions.
Perfect.
Oh, hold on.
I'll just give you 3 bullet points then, or 4, whatever it is here. I think if you walk away from this with a few take homes, one is that galvanic anodes can be used or can be designed to provide whatever level of corrosion protection you want. You just need to select what the criteria are. I would argue that design is important to ensure that you're getting the long-term protection, particularly if that's what you want. And the design needs to consider a number of factors, and some of the ones that we've talked about today are listed here, which don't need to repeat. The service life I think this is one thing that's changing over here, and maybe will in Australia as well. Service life, I think, needs to be defined during the design stage so that the design can be made consistent with what the design objectives or the service life objectives are. And I would argue that performance-based specifications are recommended, and in the long term, they're the better way to go. So no more questions. Thank you very, very much for your time. And I think we're just past your allotted time frame.
Yeah, we are. And yep, no more questions, David. So I think everyone's had their queries answered. Fascinating talk as always.
Well,
are we going to? Do we expect to see you back at Sydney at the Corrosion conference in Australia anytime soon for any of our corrosion?
Yeah, it would be great. I don't have any plans, travel plans to Australia at this point yet, although a number of international things are starting to happen, so that's good. I've made, well, I don't count going to the US as international somehow here, but made one trip to the Middle East here recently, and I'm making another one back to Eastern Europe here shortly, and some stuff later in the fall. Yeah, so hopefully I'll get back there, if not later this fall. Certainly hope, maybe over winter, by the spring, it would be good to do some things in person.
Excellent.
Yeah.
All right. Thank you for your time again, David, and thank you everyone who has attended.
Yeah, and if anyone has any questions, feel free, you can drop me an email, and happy to try and answer or provide background information if you want.
Fantastic.
Thank you.
Thanks, guys.
Have a great day. I'm going to go home to bed.